Hello, welcome back to CS561 algorithms and their analysis. So in this video, we're gonna continue our topic in dynamic programming using the rod cutting problem as an example. So last time we ended in the place where we came up with a recursive solution for the rod cut problem, which we will see later that the recursive solution is not a efficient one because it repeatedly solves the same or overlap subproblems over and over again, resulting in a very large or very bushy recursion trees. So that's basically why the original the recursive implementation of rod cutting algorithm is not a good one. So we'll need to turn to dynamic programming to uh, solve the problem efficiently. So first, let's have a quick review of the rod cutting problem. And the problem itself is that we want to maximize the profits out of a table that basically tells us how much price for the rod steels of each length. Okay, so we are given this table information um, that tells us how much we can sell for the short segments of steel, and the goal is to um, maximize the profits given a inputs or a given input rod of length n, and we'll need to choose the optimal way to cut the rod into several pieces that maximize the revenue. Okay, and we will call or return this maximum revenue in Rn. Okay, so R stands for revenue, and the N, the subscript, is for the input length. Okay, so that's the setup of the problem. Okay. So, and I will skip this page. This is the simple example of cutting rod, a short rod. And so we can represent our solutions in this addition expression. Okay, and let me turn to this page. Okay, so in general, we can express the optimal revenue from a rod of length n in terms of the optimal revenues from shorter rods. Okay, so here we have introduced the idea of the so-called optimal structure of the problem. Okay, so which basically says that the solution to the original problem can be obtained by solving the subproblems of the same nature. Okay, so in this case, we can solve Rn, which is the maximum revenue of the rod of length n by choosing among a bunch of values, choosing the maximum number out of these combinations, out of Bn, which is the price of selling this rod as a whole, and the second item, R1 plus Rn minus 1 is the revenue of is the summation of the maximum revenue of the first segments and the rest of the set of the rod. Okay, so let me see if I can find a pen here. Okay. I need a laser pointer. All right. Okay. So this R1 plus r n minus 1 is a combination of two subproblems. The first subproblem is to get the maximum revenue out of the first subpiece or first segment of length 1. And the second subproblem is to get the maximum revenue out of the second segment. Okay? So we have a simplified form of this optimal structure. Okay? So we don't need to actually solve the first one. Actually, we can simplify the so-called optimal structure into this form. Okay, we can first cut the piece of length to the left and only solve the right-hand remainder. Okay, that means only the remainder on the right side needs to be further cut or further divided. Okay, so the problem becomes choosing among this bunch of values, pi plus r n minus I, and I ranges from 1 to n. Okay, so the difference from this optimal structure from the previous one is that here we replace the ri with pi, means that we don't solve the problem on the left side. We just look at the price in the table. Okay, so yeah, so last time we introduced the recursive implementation here, and this is a quite straightforward recursive implementation, and key lies in line 4 to 5 with a for loop that ranges from all possible cut positions from 1 to n. Okay, and then it chooses the maximum value among all possible combinations. Okay, so when I is 1, we are comparing q, which is negative infinity, with p1 plus cut rod of p and n minus 1. Okay, and then this recursive call cut rod p of n minus 1 will also incur or call another for loop from I equals 1 to n minus 1. So that's the nature of the recursive call. Okay, so the problem of this recursive call is that we are repeat the same problems over and over again. So simply by giving it a number like input number like n equals 4, we can find out that the initial call cut rod of p over 4 will result in these following or subsequent calls on 3 and 2 and 1 and 0, and the call on 3 will also result in the calls on 2, 1 and 0, and the call on 2 will result in call on p on 1 and 0. Okay, so you see that I highlighted the same calls with same color, which means that the cut rod problem on length 2 is solved twice in this case, okay? And the problem on length 1 is solved 3 times, and the problem of length 0 is solved 4 times, which takes up a lot of time, way more than necessary, because for the same problem you only need to solve it once. You don't need to use a recursive call without considering or without remembering whether the problem has been solved or not. Okay? So the running time for this recursive implementation is really slow, just like we have demonstrated how slow the recursive implementation of Fibonacci problem is. Okay, so the recursive trees can be used to demonstrate how many overlap or repetition the subproblems are there. Okay, so we can basically prove that a recursive tree like this will have a solution of total running time at the scale of this exponential function, so which is a extremely slow function, or I mean, it grows really fast. Okay. It's really inefficient algorithm. Okay, so that's why we will need a dynamic programming solution for this rod cutting problem. Okay. Okay, so there are two types of dynamic programming approaches or solutions to the rod cutting problem: the top-down one, or the bottom-up one. So we'll start with the top-down approach. Okay, so this approach, it's methods with memorization. Okay, so you use a kind of a data structure like array or hash table to save the results for each subproblem. Although the overall structure is also a recursive algorithm, but it's not a dumb recursive or naive recursive solution that didn't do all the memorization. Okay, it's a kind of a smarter recursive algorithm. Okay, so this algorithm will first check whether it has already solved some problem. This is actually the key to the approach, because that's the nature of the dynamic programming. We need to know whether we have solved the subproblem before, and if yes, that means we don't need to solve it this time. We just return the value from the data structure in which we save the results, like the array or the hash table. Yeah. If not, then we do need to compute the solution at this time. But after we compute it, we will need to remember to save it to the array in case we will need it in the future. Okay. So there's a term in our textbook that calls this kind of dynamic programming procedure is Memoized. Okay, it's not memorized. I guess it's just a special jargon, special term in this algorithm study, in the field of algorithm studies. Okay. So let's look at the implementation of this top-down method. Okay, so we will need to have used two procedures. So the first one is called Memoized cut rod function. Okay, and it basically calls another function called Memoized cut rod auxiliary function. It's or a helper function. So what actually solves the results lies in here in this auxiliary function. Okay. So what the function of this procedure, of this memorized cut rod, is to first initialize the array R. Okay, and R, remember, we use R to stand for revenue, okay, which will be used to store the maximum revenues for input lengths from 0 to n. Okay, so in order to know Rn, which is our target because our input is n. We want to know Rn, but in order to know Rn, we will need to first know from R0 to Rn minus 1, and that's why we will need this new array. Okay, and we initialize this for loop, just initialize all values or elements in this array to infinity, negative infinity, or we can say it's unknown. Okay, and then we just simply return the result from another auxiliary function. So this is quite straightforward initialization procedure. So what the really magic is in this helper procedure. Okay, so it's called Memoized cut rod aux. So it takes the table, the price table P, the input N, and the auxiliary array R as inputs. Okay, so this R is first initialized here before this auxiliary function takes it as inputs. Okay, so if we look at this procedure, it looks very like the naive recursive implementation of cut rod. Okay, so the first two lines is an if statements, okay, which basically checks if the solution. Okay, let me remove my camera a little bit. I'm blocking the code here. Okay, I will move it here. Okay, so from line 1 to line 2, right? So it just checks if the result that we want is already known. Then if yes, and that's the best, and we can just return it. Okay, but if not, we will go through the rest of the lines. Okay, so here from line 3 to line 7, it looks pretty like the cut rod function. Okay, the original recursive cut rod function. Okay, if the input length is 0, then it sells for nothing, so we'll mark the revenue as Q equals 0. Okay, and if not, then we will use Q as a temporary variable, which will be used to hold the maximum value among a bunch of combinations like this. Okay, and this each combination is the results of combining two subproblems. The first subproblem is the price of selling the input rod at the left, okay, which is the price from the, which is the value from the price table, and the second subproblem on the right is the results of solving it with the same function Memoized cut rod aux on shorter inputs, which is n minus I. Okay, so if you look at the line 7 and compare it with the code in the recursive cut rod function, they are very alike. So this is a recursive call, right, to this helper function, recursive call. Okay, and after the for loop terminates, Q is the maximum value among a bunch of combinations. So we will save the Q into Rn. Okay, and afterwards we will return Q. Okay, so I guess what's different is what this function is different from the cut rod, recursive cut rod, is first of all line 1 to line 2. It checks whether the solution exists. Okay, and another difference is at line 8. Okay, so it says after finding the maximum revenue, which is in Q, we don't just directly return it. Before we return it, we need to save it into Rn. Okay, we save it into a helper array because this result may be needed for in the future computation. Okay, we will go through a simple example in the next, actually a couple of examples in the next few slides. Okay, so now let's look at a simple example that takes the inputs of 2 to see how the procedure of the memoized version of CutRod runs. Okay, so here's the code, the helper function for the memoized CutRod. Okay, and the table here is the P table. Okay, the P contains the information here in the table. It tells us the price for P1, P2 to P10. Okay, and assuming that the N is 2 in this case. Okay, so remember that before we run this CutRod code, we will have to first run the memoized CutRod to initialize, right? Before we run the helper function, we need to initialize the R array into unknown values. Okay, so that's why we will, before we run the helper function, we will have R's in or infinity, negative infinity values or unknown values. Okay, and because our input is 2, that's why the R has 3 elements from 0 to 1, from R0 to R1 to R2. Okay, and the initial call is Memoized CutRod aux with n equals 2, right? And then we will go through the code. And obviously from line 1 to line 2, this if condition is not satisfied because everything in R are unknown now. Okay, so we'll skip, after the initial call, we'll skip 1 or 2. Okay, and in this call n is 2, so we also skip line 3 and 4. Okay, so we'll start from line 5, and it will incur the for loop, right? So from line 5, we have q equals infinity, and from line 6, we'll start the iteration. Okay, and because n equals 2, this iteration, this for loop has 2 iterations, right? I equals 1 to I equals 2. Okay, so we look at the first iteration when I equals 1. We are doing this computation. Q equals the maximum value among infinity, right? Because Q is infinity at first, right? Q is infinity and I is 1, so it's the result of P1 plus memoized CutRod aux on P n minus 1, which is also 1, and R, right? So that's the result. That's the code being executed in first iteration of the for loop. Okay, so there's a recursive call here. So now let's look at what this recursive call will incur, right? So to this recursive call, its n is 1. Okay, so we will go into this recursive call, dive deep into this recursive call with n equals 1. Okay, and in this call, we will also skip the code from line 1 and line 2, right? And also skip line 3 into line 4 because n equals 1. And within this call, we will also initialize the q to in infinity. Okay, but this time I color this q within this recursive call in different color because this q in blue is different from the q that we initialized at the upper level. They are different queues. Okay, so this blue queue is only exists within the scope of the recursive call here. Okay, so within this recursive call, the for loop only has one iteration, right? Because n is 1 here, and the for loop will range it from 1 to 1. Okay, so the statement in the for loop is p1 plus Memoized cut rod ox with p0. Okay, this is 0 because here is n minus I, which is I1 minus 1, 0. Okay, so there's a third recursive call here, Memoized cut rod ox on p0 and R. So now let's go deep again, go even deeper into this third recursive call. Okay, so this is a special value now. It's R n equals 0, right? So when n is 0, from our code we will see that if n equals 0, the queue will be 0. So of course this queue will be a third queue because this queue exists within the third recursive call, the second recursive call here, right? So it's different from the blue queue and the black queue as well. So within this this second recursive call, queue is 0, right? And we'll skip the line 5 to 7 code, right? Because n is to this recursive call, n is 0, and we will store. We'll go to line 8 and store the queue into the corresponding Rn, which is R0. Okay, so we'll change the value of R0 to 0, which is the current queue. Okay, so this results in the update on the R array, which changes the value of R0 from infinity to 0. Okay, so that means we have solved a problem of rod cut on the input length of 0, and we have the solution, which is also 0, and we need to save it for later use, right? So that's why we update the R table. Okay, and then we will return the Q value, the orange Q. Okay, so we'll go after R0 is saved, we'll return the Q. We'll go to the upper level, which is in the blue recursive call, our first recursive call. Okay, so in this blue recursive call, we go to these statements. So we are choosing among an infinity value and the results of p1 plus some q, which is 0. Okay, so it's the result of choosing a maximum around infinity and 1 plus 0. This 0 is just the orange q that got returned. Okay, so choosing among the maximum value will give us 1. Okay, which means the blue q is 1. Okay, so after the blue q is computed, we will need to save the blue q according to line 8. We'll need to save the blue q into R1. Okay, because in the blue recursive, the input is 1. That means we have solved the subproblem of input size 1 already, and now we need to save it because we may need to use it in the later time. Okay, so we solve R1 with the value of blue q. Okay, you see we update the R table again, so now we have R1, R0 and R1 all solved, and what's left is just R2, which is unknown. Okay, so after the blue recursive calls ends or returned, it will return the blue q, right? Q1. So now we go a level up again. We'll see that the black q is among the negative value, negative infinity, and P1 plus the blue Q. Okay, and the P1 plus blue Q is 2. So that's at this iteration, the black Q is 2. Okay, so we're not done yet with black Q, because in computing the black Q, we will need to have 2 iterations in the for loop. Okay, so in the first iteration, I is 1, but in the second iteration, I is 2. Okay, so now we'll go to the second iteration. Okay, so for the second for iteration here, we need to compute k, a q among the maximum of the old q. The old q is 2, right, from the iteration 1. So we're comparing the old q with the new candidate, which is P2 plus memoized rod cut ox with P0 on. Okay? So now we meet another recursive call, but remember here, this recursive call, it's already solved once in the previous iteration. The result of R0 is already here, is already 0. It's not infinity, it's not unknown. Okay? So we will directly return R0, which is 0. Okay? So in the second iteration, the computation of Q is a maximum among 2 and P2 plus 0, which is 5. Okay? So in the computation of the black Q, after the 2 for loop iterations end, Q equals 5 will be the final solution. Okay? And then we go to line 8, where we will save this Q, this final Q, into R2. And we have the table updated. We save the results. Okay? And we also return Q. It will be the results, the final solution of solving the rod cutting problem with input length equals 2. Okay? You will see that because this is a short example, and we can clearly identify that where the dynamic parts, where the efficient part happens is here and here. In the first within the first iteration, in its orange recursive call, we solved the subproblem of size 0 once, and we saved it. Right? After we saved it, we can avoid solving that again by just retrieve the saved results R0 and directly do the computation. It saves us some additional cost of actually calling this function using stacks in a recursive way. So that's where the efficiency comes from. Okay, so that's the very first example of running Memoized top-down Memoized cut rod function on the input length of 2. Okay, now let's just look at a slightly longer input. So say we have input length equals 3, and we have the same table here. So we'll initialize the R into a empty or unknown arrays of 4 elements from R0 to R3. Okay, so the initial call of Memoized cut rod ox with n equals 3 will result in a incur a for loop, right? So before the for loop, Q is initialized to infinity, and in the first iteration on the for loop, I equals 1. Okay, and we will call in the for loop, the statement of for loop will be this computation. Q will be the maximum among a negative infinity and P1 plus memoized cut rod arcs on n equals 2. This 2 is 3 minus 1. Okay. So this recursive call, the blue recursive, will result in a deeper for loop, which we just saw before in the previous slides, because the input size is 2. And within this call, there will be another for loop, right? Which I highlighted with the blue color. In this blue for loop, the range is from I equals 1 to I equals 2. Okay, so when I equals 1, so this I is different I from the upper level in this blue for loop. When I equals 1, the blue Q is the maximum among the infinity and the P1 plus memoized cut rod arcs P1. Okay, and within the second iteration of blue for loop, I equals 2, and the Q will be among the maximum value among 2. So this 2 is from here, is solved from the previous iteration. Okay, well, I skipped the process where I dive into the details of this memoized cut rod arcs with n equals 1, which needs to call the memoized, will call the same function on n equals 0. But we did that step in the previous slide, so I'm not going to do that again in here. But the result of this statement is that the temporary value of Q becomes 2. And this Q2 will pass along into the second iteration of the blue for loop, which will be passed here. Okay, so Q will be a comparison between these two, this old value of Q and this new value, which is P2 plus the memoized cut rod arcs function on n equals 0. And this 0 inputs problem is already solved in this previous iteration. Okay, so this is actually a very efficient call because it's just returned R0. So Q will be 5 here. Okay, that's why the maximum Q in the first iteration of the black for loop is among the negative infinity and the result of P1 plus 5. Okay, that's why the first Q is 6. The first candidate for Q is 6. Okay, but remember, for the black for loop, we have 3 iterations. I equals 1, 2, 3, right? So in the second iteration, I equals 2. And in this second iteration, we do the same thing. We compute Q among the older value 6, which is here, comes from here, 6 among, and compare it with P2 plus memoized rod cuts on n equals 1. And remember that here, this one is already solved. Okay, it's already given here, 2. Okay, so we don't need to solve it again. We just return the value, retrieve the value from R. We just retrieve R1 is 2, retrieve 2, and plus P2. P2 is 5. Okay, so R1 is 1. I'm sorry, R1 is 1, and then we plus it with P2. P2 according to the table is 5. So the result is comparing among 6 and 6, which is also 6. Okay, and in the third iteration, I equals 3. Okay, Q is among the maximum of the older value of Q, 6, and P3 plus memoized cut rod arcs on the subproblem of 0. Okay, which should give us 0. Okay, so it's among 6 and 8, which is 8. So the memorized version should return Q equals 8 because 8 is among the maximum values, is a maximum value. Okay? So the results of the R is updated, right? So this new R table tells us that the recursive, the solution to the subproblem of 0 is 0, to the problem of 1 is 1, to the subproblem of 2 is 5, to the subproblem of 3 is 8. So before, if you don't look at, okay, I'm blocking myself again. Let me remove the camera. Sorry about that. So if you look at this new table, R0 to R2 is the same from the previous slide. It's from the previous problem with input n equals 2. Okay, and what's new here is the new array, which is the solution to the subproblem of length 3, which is 8. Okay, so it's basically the same steps, but just with more deeper recursive calls. Okay, so hopefully using these inputs from n equals 2 to n equals 3, it helps you shape a big picture of how this procedure runs with a top-down manner. So now we will talk about the second type of solutions to the dynamic programming approach to the rod cut problem. So it's called the bottom-up dynamic programming. So you may have noticed that in the previous bottom-down value, we use the recursive calls to the function, right? We define some auxiliary function, and within the how we solve the problem is to first check if the problem is already solved. If not, then we will use the recursive calls to solve the problems of smaller sizes, right? So this bottom-up approach, I think, is more straightforward because it recognizes the fact that in a dynamic programming problem, in order to solve the original problem, we need to first solve all possible smaller subproblems, and that's a very important condition that we need to satisfy, right? In order to solve the so let's recall the example we use for the rod cut problem with n equals 3, right? In order to get R3, we need to first get R2 and R1 and R0. There's an interdependencies relationship there. R3 depends on R2, and R2 depends on R1, and R1 depends on R0. So why not we set up our algorithm in such a way that we can solve the smallest subproblems first, and then solve the bigger one, and then bigger one in a bottom-up manner. Okay, so that should help implement more straightforward algorithms instead of using recursive calls. Sometimes recursive calls is just not that obvious or self-explanatory. Okay, so in this bottom-up approach, we need to solve smaller subproblems first, because any problems that's bigger one depend on the smaller subproblems. Okay? We start from the smallest case. Okay? And when solving a particular subproblem, we need to make sure that all the subproblems, all the smaller subproblems, are already solved. Okay. Okay. So here's a typical implementation of the bottom-up approach of a rod cutting problem. Okay. So it takes the inputs as the price table P and the input size N as inputs. So it doesn't take the R as input because R is defined within. So this time we define the revenue array within the function itself. It's no longer initialized outside the procedure. Okay, so we'll initialize the revenue table from 0 to R0 to Rn. Okay, so this is the same as the top-down method, right? And this array will be used to save the solutions to subproblems. And we initialize the smallest case to 0, okay, because we know that its solution is 0. Okay, so now what's important is that from line 3 comes a for loop. Okay, so there's an outside for loop that iterates j from 1 to n. So j is the loop counter. J iterates from 1 to n. So this j, this outside for loop, it stands for the current subproblem that we are going to solve. Okay, so the order of the sequence matters. It ranges from 1. Iterates from the smaller value 1 to the bigger value, from 1 to n, in that increasing order, because we want to use that order because the bigger problems depend on the smaller problems. Okay, so we will need to first solve R1, and when R1 is solved, we solve R2, and then until we solve Rn. Okay, and within each iteration, we use similar method. So how we solve Rj, for each j, how we solve that specific subproblem of size j. Okay, so j refers to, j represents the size of the subproblem. Okay, so how do we solve the subproblem j? We need to use the code from line 4 to 6 to solve the subproblem of size j. Okay, so from line 4 to 6, it solves the subproblem of size j, and it's quite similar to what we did in the original recursive rod cut procedure, right? We define some intermediate or temporary variable q initialized with negative infinity, and then in order to solve the problem of size j, we'll need to use a secondary or second for loop that ranges from 1 to j, because we are dividing that problem of size j into its own subproblems, right? And there are j possible ways to divide a subproblem, to divide a problem of size j, right? Either we cut size 1 and solve the remaining parts, or size 2 plus solve the remaining parts. That's very similar. That's just exactly the way that we did for the recursive call of cut rod. But the only difference that is here, there's no recursive call here. Okay, so q is a maximum among q and pi plus r j minus I. So j minus I is a remainder when you cut I from j, right? So you cut I from j, what's remaining is j minus I. And here, it's just we just use the index of j minus I to retrieve the optimal solution to that subproblem. But we don't recursive solve it, because we know that this subproblem must already be solved. Okay, because within this iteration, within the j iteration, the I ranges 1 to j, which means that j minus I must be a smaller subproblem than j, and any smaller subproblem is already solved, which means we can just directly retrieve the value. Okay, so we just look up the results from the array rj minus 1 instead of making a recursive calls to solve it. Okay, and we know that a subproblem of size I is always smaller than a subproblem of size j. Okay, and after the secondary for loop terminates, which means we already know the solution of j, so we will save it to rj. Okay, and this rj will be later used in the next iteration of the external j for loop. And after the external loop for loop ends, we'll return the final solution of Rn. So we'll use a simple example as well to showcase how this procedure runs. Okay. I personally think that this is a more easier to understand than a top-down method. Okay, so now let's look at how this bottom-up procedure runs with a simple input with length 3. Okay, so let's assume that a input length is 3, and according to the algorithm, we'll first initialize the revenue array into all zeros from R0 to 3. And the for loop ranges from 1 to 3. In the first iteration of the outside loop, j equals 1. And the iteration of the internal for loop iterates from I equals 1 to 1, because j is also 1. So there's just one iteration in the internal for loop. And within this internal for loop, q is computed among the the initial value of infinity and p1 plus r0, and 0 comes from j minus I, which is 0. Okay? And because this r0 is initialized to 0 and the p1 is 1, so choosing among the maximum of infinity and 1 results in 1. Okay? And this 1 is exactly the solution to the subproblem of size j, which is size 1. So we will save it into R1. Right? So after this first iteration of j equals 1, we will have the revenue table updated with R1 to a new value. Alright, and then we will enter the second iteration of the j for loop. So j equals 2. And when j equals 2, the internal I for loop has 2 iterations for I equals 1 to 2. Within the first iteration for I equals 1, then the q is the maximum among negative infinity and the p1 plus r1. And luckily, we have r1 already solved in the previous iteration of the j for loop. So we can directly retrieve R1 by looking at the table, right? It tells us it's 1. Therefore, the Q should be 2. And in the second I for loop iteration, Q is a maximum among 2 and the P2 plus R0. And R0 is also already known. So we have Q equals 5. So we are choosing among the maximum value. The resulting Q would be 5, right? And we will need to save the results into R2 because that's the solution to the subproblem of size 2. After the second iteration of j loop, we will have R2 updated as well, which is 5. Okay? So into the final iteration, the third iteration of the j loop, we will have 3. For the internal for loop, I for loop, we will have 3 iterations for I equals 1 to 2 to 3. Okay? For the first I iteration, we need to look at R2, which is already solved in the previous j iteration. Okay? That's why Q equals 6. And for R1 and R0, we do the same thing. So after the j, after all I iteration ended, we will have R3 equals 8, and then we save it again. We save the result into the revenue table. Okay, so that's and finally, after all the j iterations end, we'll return the last element of the revenue array, which is 8 in this case. So you see, this is a quite straightforward demonstration of how the bottom-up procedure runs with a simple example. And the key is that we organize the order of how subproblems are solved. We make sure that the smallest subproblems is solved first, and we solve the smaller ones first after and before we solve the bigger ones, so that when we solve the bigger ones, when we need the results of smaller ones, we can directly retrieve the values, retrieve the solutions from the array. And that's it for the two approaches, both top-down and bottom-up solutions, dynamic programming solutions to the rod cut problem. So I will suggest you to read the code and run. If it's not clear yet, you can run some simple examples on a paper, and or you can play the slides for several times so that you have all pieces connected. Okay, it's not I don't think it's easy to like directly understand it all at once when the first time you see the code, but the ideas will finally connect when you run through some examples. Okay, so now let's quickly look at the running time analysis. So it's tricky because it's easy to understand the bottom-up way. And if you look at the code, it's just two for loops, right? The range of the first for loop is from 1 to n. And the second for loop is from I to j, right? So it's very like the insertion sort, right? So it makes sense that the running time is bounded by the quadratic function for the bottom-up function, and it's basically the summation of a arithmetic series. And what's interesting is that for the top-down method, the running time is also bounded by a quadratic function, but it's not straightforward, or it's not obvious to see because it's a lot of recursive calls involved. So the textbook says we will need to use the aggregate analysis method to analyze the runtime, but it's not required here in our class. Okay, so I think that's it for the dynamic programming parts so far for today's lecture, and then in the next video I will talk about the questions in our first midterm exams.